NASA's Pandora mission and companion CubeSats, a scientific overview of exoplanet atmospheres, stellar activity, and high-energy transients. On the 11th of January 2026, NASA achieved another milestone in space exploration. A SpaceX Falcon 9 rocket launched from Vandenberg Space Force Base in California, carrying NASA's Pandora small satellite, along with two innovative CubeSats, BlackCAT and SPARCS. This rideshare mission, known as Twilight, deployed these payloads into a sun-synchronous orbit, a special path that keeps the satellites in near constant sunlight for stable observations. Just 2 days later, on January 13, mission controllers confirmed full signal acquisition from Pandora. The spacecraft is now in commissioning phase, a 1-month period of testing and calibration before beginning its primary science operations. These missions represent NASA's commitment to cost-effective, high-impact astrophysics. They address fundamental questions. What are the atmospheres of planets beyond our solar system like? How do stars influence planetary habitability? And what can we learn from the universe's most energetic explosions? In this video, we provide a detailed scientific overview of each mission, their objectives, technical designs, and expected contributions to astronomy. The Pandora small satellite, characterizing exoplanet atmospheres. Pandora is the flagship payload of this launch and the first mission in NASA's Astrophysics Pioneers program. Selected in 2021, Pioneers missions have a strict cost cap of $20 million and focus on compelling science with innovative, lower-cost approaches. Pandora weighs approximately 325 kilograms and features a novel 45-centimeter 17-dash all-aluminum telescope developed collaboratively by Lawrence Livermore National Laboratory and Corning Incorporated. Its near-infrared detector is a spare unit originally built for NASA's James Webb Space Telescope. The mission operates in low Earth orbit at about 600 kilometers altitude in a sun-synchronous configuration that enables consistent viewing conditions. Pandora's core scientific goal is to study the atmospheres of at least 20 transiting exoplanets, planets that pass in front of their host stars from our line of sight. Transiting exoplanets allow astronomers to use transmission spectroscopy. Starlight filters through the planet's atmosphere during transit, and gases absorb specific wavelengths, creating detectable fingerprints of molecules like water vapor, oxygen, or methane. However, a major challenge exists. Stellar surfaces are not uniform. They feature active regions such as spots, faculae, and plages, brighter or darker areas that rotate, evolve, and can contain the same chemicals. For example, water vapor that astronomers seek in planetary atmospheres. These stellar features can mimic, mask, or contaminate planetary signals. Pandora addresses this stellar contamination by conducting long-duration, multi-wavelength observations. For each target, the spacecraft performs 10 full transits, with each observation lasting 24 hours. This totals over 200 hours of data across the prime 1-year mission. Visible light photometry monitors the star's brightness variations outside and during transit, while simultaneous near-infrared spectroscopy captures atmospheric absorption. By combining these datasets, scientists can separate stellar variability from true planetary signals. Pandora targets exoplanets previously discovered by missions like NASA's Kepler, Test Transiting Exoplanet Survey Satellite, and JWST, many of which are known to have potential water or hydrogen-dominated atmospheres or hazy, cloudy envelopes. The data will refine interpretations of JWST observations and help prioritize targets for future missions searching for biosignatures and habitable worlds. All Pandora data will be publicly available through NASA's archives. The mission is led by Principal Investigator Elisa Quintana at NASA's Goddard Space Flight Center, with key contributions from Lawrence Livermore, National Laboratory Project Management and Engineering, NASA's Ames Research Center, Data Processing, the University of Arizona Mission Operations, and multiple university partners. Here are some visuals of the Pandora spacecraft and its telescope design. BlackCAT, probing high-energy transients and gamma-ray bursts. BlackCAT, or Black Hole Coated Aperture Telescope, is a 6U CubeSat measuring 30 by 20 by 10 centimeters, roughly the size of a shoebox. Developed and operated at Pennsylvania State University under lead Abe Falcone, with contributions from Los Alamos National Laboratory and Kongsberg Nano Avionics spacecraft. Funded through NASA's Astrophysics Research and Analysis Program. BlackCAT features a wide-field coated aperture X-ray telescope with novel hybrid CMOS detectors sensitive to soft X-rays. The coated aperture mask encodes incoming X-rays to produce images with sub-arc-minute localization, precision, and a field of view of about 0.85 steradians. The mission focuses on detecting and localizing high-energy transient events, particularly gamma-ray bursts. GRBs are the universe's most luminous explosions, releasing energy equivalent to the sun's lifetime output in seconds. Long-duration GRBs arise from massive star collapses, while short-duration ones often result from neutron-star mergers, events that also produce gravitational waves. BlackCAT is optimized for high redshift GRBs from the early universe, providing insights into cosmic evolution, black hole formation, and heavy elements synthesis. It will also monitor X-ray flares from supermassive black holes and active galaxies and other fleeting phenomena. As part of NASA's Transient Monitoring Network, BlackCAT will generate rapid alerts for multi-messenger follow-up by ground and space-based observatories. This low-cost platform demonstrates advanced X-ray detection technology for future, larger missions. Here are images illustrating BlackCAT's design and the types of cosmic events it targets. SPARCS, monitoring stellar activity and exoplanet habitability. SPARCS, the Star Planet Activity Research CubeSat, is another 6U CubeSat led by Evgenia Shkolnik at Arizona State University, with participation from NASA's Jet Propulsion Laboratory, UV detectors and electronics, and Blue Canyon Technologies spacecraft bus. Selected through NASA's CubeSat Launch Initiative, SPARCS is equipped with dual ultraviolet detectors covering far UV 153, 171 nanometers and near UV 260, 300 nanometers bands. The mission monitors flares, star spots, and other activity on low-mass stars, primarily K and M-type red dwarfs, which comprise about 70% of stars in the Milky Way. These cool, dim stars have close-in habitable zones, making their planets prime targets for habitability studies. However, red dwarfs are highly active, producing frequent and intense flares that emit strong ultraviolet and X-ray radiation. Such activity can erode planetary atmospheres, strip ozone layers, damage potential biosignatures, or, in some cases, drive prebiotic chemistry. SPARCS will observe 20 target stars continuously for 1 to 3 full stellar rotations, 5 to 45 days each, over its baseline mission. This provides time-resolved spectral slopes, flare intensities, and evolution data, the first long-duration UV monitoring of low-mass stars. The results will inform models of space weather around exoplanets, guide JWST atmospheric observations, and assess habitability for test-discovered worlds. SPARCS exemplifies how CubeSats deliver targeted, high-value science at low cost, while training the next generation of engineers and scientists. Here are visuals of the SPARCS CubeSat and UV observations of stellar flares, broader impact, and NASA's innovative approach. These 3 missions, Pandora, BlackCAT, and SPARCS, launched together on the same Falcon 9 rideshare, demonstrate NASA's strategy for accessible astrophysics. CubeSats and small satellites lower barriers, enable rapid development, and foster collaboration across universities, national labs, and industry. Pandora complements JWST by providing stellar context for atmospheric studies. BlackCAT advances time-domain astronomy and multi-messenger science. SPARCS addresses a critical gap in understanding stellar influences on habitability. Together, they contribute to NASA's core questions. How does the universe work? And are we alone? All data will be openly available, accelerating discoveries worldwide. As commissioning continues in January 2026, stay tuned for first light and early results from these pioneering instruments. Thank you for watching this scientific overview. Subscribe for more updates on space missions and share your thoughts in the comments. Which aspect of these missions excites you most? Until next time, keep exploring the cosmos.